In section 2.3, we started talking about getting information from the graph of a function. And there are a couple pieces of information that we're going to get by looking at a graph, whether the graph is hand-drawn or we put it in our calculator. We're going to look at domain. Remember, domain is your x coordinates, your input. Range, your y coordinates, your output. We're going to look at something called local maximums and minimums. Those are going to be high and low points on your graph. We're going to look at intervals of increasing and decreasing. If we read a graph from left to right and you put your pencil on the graph, if your pencil's going up, your graph is increasing. If your pencil's going down, your graph is decreasing. It's a pretty simple concept. Let's talk about looking at a graph and extrapolating information from it. The function t graphed gives the temperature between noon and 6 p.m. at a certain weather station. Find t of 1, t of 3, and t of 5. Well, t of 1, we're going to go to 1 on the x-axis, and we're going to find out where it hits the graph. Well, it appears to hit here. So if the input's 1, the output appears to be about 25. T of 3, here's 3. So then I go to see where it hits the graph. T of 3 looks like it has an output of about 30. And T of 5 looks to have an output of about 20. Which is larger, T of 2 or T of 4? Well, let's look at see where T of 2 is. T of 2 is up here, and T of 4 is below it. So T of 4 must be larger. Find the value or values of x for which t of x is equal to 25. Well, now we want to look at where the output is 25. And the best way to do that is to draw a horizontal line through 25. Well, it appears that the graph hits 25 at about x is 1 and x is 4. Find the values of x for which t of x is greater than or equal to 25. Well, we've already drawn a horizontal line at 25. We want to know where is that graph higher than that line. Greater than means above. Well, we can see that the graph is above 25 from here to here. So we would say from 1 until 4. This graph is greater than or equal to 25. That means between 1 p.m. and 4 p.m., which does make sense because in general, the weather tends to be warmest between 1 p.m. and 4 p.m. Now, let's graph a function on our calculator and then attempt to find the domain and range. Well, if you graph this function, square root of 4 minus x squared on your calculator, and you play with the window so that you have a nice picture on your screen, you're going to see something that looks like this. You're going to get a nice little semicircle from -2 to 2 when it goes up to +2 on the y-axis. So what's the domain? Well, the x values only go from -2 to +2. And the graph exists nowhere else. If I were to look at 3, I would not be able to go up or down to try to find where it hits the graph because the graph doesn't exist there. So we say that the domain is from -2 to +2, inclusive, because at -2 or +2 you get 0, and the square root of 0 is 0. For the range, I only see the graph from here to here. This is 0 and this is 2. So we say that the domain, or the range, is from 0 to 2, inclusive. Remember, we use the brackets for inclusive and parentheses for non-inclusive. Now let's talk about intervals of increasing and decreasing. If you read a graph from left to right and you put your pencil on the curve, so I'm going to start with my pencil at point A. The first thing my pencil does is it goes up, where the y values are getting more positive. We say that that is an interval of increasing. So if we call this point A and we call this point B on the x-axis, we would say that the graph is increasing from A to B. But then at B it takes a turn, and then my pencil starts going down until it gets to C. Well, if the pencil's going down, we say that it is decreasing. We'll call that point C. So the graph is decreasing from B to C. And then at C, it starts going back up again until it gets to D. So we say the graph is increasing from C to D. Now, I had mentioned in class the difference between using a bracket and a parentheses. Now, you'll notice at point A here, it's a distinct endpoint. So using this bracket is important. However, here at point B, the graph takes a turn. It doesn't stop there. It just takes a turn there. And because at the actual point B, we say that the graph is neither increasing or decreasing, you can also use a parentheses rather than a bracket. However, I'm not going to take off points for that. I'm more concerned that you find the actual interval. Let's look at an example. The graph gives the weight W of a person at age X. Determine the intervals on which the function W is increasing and the intervals on which it is decreasing. So I'm going to take my pencil and I'm going to start on the leftmost part of the graph. Well, clearly it's increasing. Where is it increasing? Well, it's increasing from 0 to, it looks like, about 25. Well then, from 25 to 35, it is neither increasing nor decreasing. It remains constant. And then from 35 to 40, it increases again. Then, from 40 to 50, the graph is decreasing because my pencil went down. And then from 50 on out, it remains constant. So the only intervals of increasing, decreasing that I have are from 0 to 25, it increases, from 35 to 40, it increases, and from 40 to 50, it decreases. In this next example, the first thing that you're going to do is you're going to sketch the graph of f of x equals 12x squared plus 4x to the third minus 3x to the fourth. And you're going to do it in your graphing calculator, and you're going to change the window until you have a nice sketch in your window. And it should look something like this. The next thing that I want to find is the domain and range. So let's find D and R. Now, the domain, remember, is what x values can I plug into this function. Well, even though it appears as if these graphs are just kind of going straight down vertically, they're not. They're still moving along the positive x-axis and moving along the positive or the negative x-axis, even if it's minutely. So in general, we'll say that the domain is all real numbers. However, the range is not all real numbers. I want you to notice that the highest this graph goes is up to 30. That's 40. And all the rest of the graph is below that. So we would say that the range, is y is less than or equal to about 30. Or the other way of writing it is that it starts at 30 and it goes to negative infinity. parentheses. Last but not least, let's find the intervals of increasing and decreasing. Well, so if I go from left to right, first this graph is increasing. Where is it increasing? Well, it starts at negative infinity, and it appears to be increasing until it hits about negative 1. Negative 1 to 0, it takes a turn where the graph is going down, so it's decreasing from negative 1 to 0. And then at 0 up until about 2, it appears to be increasing again. And then from 2 on out, it's decreasing forever. So those are the intervals of increasing and decreasing. Let's do another example. Let's sketch a graph of f of x equals x to the 2/3. Graph it in your calculator. Play with the window function, and you're going to get something that looks like this. Something like that. Now, let's find the domain and range. Well, the domain, again, is what x numbers can you plug into this and always get a number out. Well, you can raise any number to the 2/3 power. An integer, a fraction, a decimal, positive numbers, negative numbers. So we say that the domain is all real numbers. The range, however, is not all real numbers. You'll notice that the lowest that this graph goes is the x-axis. And then all the rest of the graph is up from there. So the range is y is greater than or equal to 0, which in interval notation is 0, comma, infinity. Now let's talk about another piece of information that we can get from looking at graphs. We're going to talk about something called local maximums and minimums. Local maximums and minimums are just high points and low points on a graph. They're bumps along the road. And we're going to use our graphing calculator to help us find the exact locations of these maximums. Now, at the ordered pair that you're going to get for a maximum or minimum, we're going to say that the max or min is the y coordinate of that ordered pair, and that y coordinate value is located at x. Let's do an example of how that works. Let's find the local minimum and maximum values of the function f of x is equal to x to the 3rd minus 8x plus 1. Now, I expect you to just put this into your calculator, and when you do, you should get some, and I'm not drawing a straight line there, you should get something that looks similar to this. Now, when you want to use the calculator to find a maximum or minimum, the maximum and minimum values are located under second trace. That's the calculate function. And we've used that before because we've probably showed you how to find points of intersection of lines. Well, this one we're going to use 3 and 4. One of them is for minimum and one of them is for maximum. So if we work from left to right, let's find the maximum first. So hit enter on the value that's, or on the word maximum. Now, when you do that, the bottom of your screen is going to prompt you to identify a left-hand bound. Well, move your cursor so that it's somewhere to the left of the hump, and then hit enter. So it locks in that ordered pair. Then you move your cursor over to the right-hand side, and you hit enter again. Now at the bottom it says guess, and you want to take a guess. So you hit enter a 3rd time, and then it'll tell you exactly at what ordered pair this is at. It is exactly at 9.71, and that maximum is located at x equals negative 1.63. Now let's go find this minimum by hitting second trace, number 3. Get your cursor somewhere to the left of that minimum, hit enter. Move the cursor to the right of the minimum and hit enter, and then hit enter again when it says guess. And you'll find out that minimum is at negative 7.71 at the x value of 1.63. Let's do one last example. A model for the food price index, the price of a representative basket of foods between 1990 and 2000, is given by the function I of t, I meaning index, t meaning time, equals negative 0.0113 t to the third plus 0.0681 t squared plus 0.198 t plus 99.1. where t is measured in years since mid-year 1990, so that t is between 0 and 10, and I of t is scaled so that I of 3 is equal to 100. Estimate the time when food was most expensive during the period 1990 to 2000. So the first thing you're going to do is put this in your calculator. And the first thing you'll notice is that you see no graph. So now you need to play with the window. Now, since time cannot go backwards, let's only work in quadrant 1. So I played with my calculator and I changed my window to look up the y-axis, and I started at 100 for the y maximum and noticed that I could see part of the graph but not all the way up. So then I changed the y maximum to 120. Then I could see high enough on the graph. But the other thing that happened was I couldn't see far enough along the x-axis, so I played with the x-axis. And when I finally got to 30 for an x-max, I got a graph that looked nice. The graph I got looks something like this. Well, I wanted to find where the maximum was at. So then I went to the maximum function under second trace, and I gave it a left bound, I gave it a right bound. When it said guess, I hit enter, and it told me that the maximum was at x is 5.15 and y is at 100.38. That means that the maximum value of I is about 100.38. It occurs when t is 5.51 years. Well, if t starts at 1990, then if I go 5.15 years, I've gone to about 1995. When in 1995 is that? Well, remember we said that this starts mid-year. Well, what's mid-year? Well, it's July 1st. And then, if this is July 1st, 0.15 times the fact that there are 12 months in a year will give me 1.8. That means it's about a month, or 1.8 months after July 1st, which would put me in August of 1995, would be when the food was most expensive between 1990 and 2000.